Hi everyone, I'm Kai Huang from University of Pittsburgh. It's my pleasure to present our work, Real-Time Neural Network Inference on Extremely Weak Devices, Agile Offloading with Explainable AI. This is a joint work with my advisor, Dr. Wei Gao at the University of Pittsburgh. With the increasing capability of neural networks, there is a pressing need of enabling real-time neural network inference on weak embedded devices to allow more intelligent decision-making. For example, neural networks can be running on wearables to detect health risks. They can also assist small drones and robots to better perceive and interact with surroundings for autonomous navigation. In smart home scenarios, neural networks can be deployed on sensors and actuators to optimize living conditions such as access control, HVAC, and lighting control. However, deploying neural networks on these small devices is very challenging because of the huge gap between these devices' weak capabilities and the neural network's high computing demands. For example, commonly used microcontrollers such as STM32 and MSP430 only have less than 1 megabyte of memory and tens to hundreds of megahertz of CPUs. But popular convolutional neural networks like ResNet50 and VG16 require over 100 megabytes of memory and 2 gigahertz of CPU to achieve 60 milliseconds of inference latency. Such a requirement may be achievable on powerful mobile devices, such as smartphones and laptops, but it is unaffordable for weak microcontrollers. To bridge this gap, researchers have used pruning, compression, and neural architecture search to reduce the local neural network complexity, where the blue blocks illustrates the neural networks. However, to fit into the local resource constraints of the embedded devices, these techniques always lead to oversimplified neural network structures and reduce the inference accuracy. Instead, a better solution to avoiding accuracy loss is to offload the neural network computation to a remote server. We usually compress the neural network input data before transmission, but the compression ratio can only be limited because aggressively compressing data will lose important information in the data and reduce inference accuracy. Later research efforts suggest partitioning the neural network and using a local neural network to sparsify the data into a more compressible feature space before transmission, which is illustrated by a small blue grid. However, an expensive local neural network is always needed to ensure such feature sparsity. The key reason for this expensive local neural network is that the existing neural network partitioning schemes apply the same learning scheme to every input data sample. Even for easier data samples, they still need to spend the same computing cost as for the most difficult data sample. Instead, our goal is to shift the rationale of neural network partitioning and offloading from fixed to agile and data-centric. Specifically, we identify different data samples' heterogeneity in the neural network inference as the importance of different data features to the neural network inference, and incorporate such feature importance into the offloading strategy. In this way, the weak device can adaptively partition the neural network inference for each data sample according to its characteristics. Based on this basic idea, we propose AgileNN, a new offloading technique that adapts the offloading strategy to each data sample. On the local device, a lightweight feature extractor will be used to evaluate the importance of each data sample's extracted features to the inference task. And these features are partitioned into important and less important features. Only the few important features will be retained locally, and their representativeness allows them to be easily perceived by a lightweight local neural network. And the less important features are less relevant to the inference task and are hence more compressible. They will then be compressed with much higher ratio and offloaded for remote inference with much lower cost. Finally, predictions from local and remote will be combined on the local device. To realize this offloading framework, we will have to address two challenges. The first is how to correctly and efficiently evaluate feature importance. And the second is how to maximize the compressibility of the less important features to be transmitted. Our solution to the first challenge is to leverage explainable AI to evaluate feature importance. Typical XAI techniques compute the neural network outputs gradients with respect to feature variables. By analyzing these gradients, XAI reports the importance score indicating each feature's contribution to the neural network prediction. However, running XAI tools at runtime is computationally expensive because gradient calculation requires hundreds of megabytes of memory, and the XAI algorithm itself may need many iterations to produce a single result. These are not affordable on small embedded devices. Instead, we migrate such online computation to offline by training an XAI-enabled feature extractor. During offline training, XAI will act as a supervisor that trains the feature extractor to output features that always produces top important features at the first K channels. So during online inference, the produced feature vector can be directly used to be split into important and less important portions. Our solution to the second challenge is to make sure that the distribution of feature importance is highly skewed, such that the importances of few top features are much higher than those of other features. Such skewness ensures that the less important features are highly redundant and can be compressed at a high ratio. We enforce such skewness when training the feature extractor by controlling the loss function with two parts, the disorder loss and the skewness loss. We first use disorder loss to ensure that the top most important features are always extracted into the first K channels in the feature vector. In particular, the disorder loss encourages the lowest importance of the first K features to be larger than the highest of the remaining features. Achieving this only requires minimal ordering efforts, so it can be learned by a lightweight feature extractor. We express the disorder loss using min and max functions, which are differentiable to compute the training feedbacks. After that, we further use the skewness loss to enforce skewness between the important and the less important features. We also use the max function to express the skewness loss. The user can set a specific objective indicated as rho for the cumulative importance of the top K features that will be retained at the local device. Based on such loss functions, the offline training procedure of Agile N jointly trains the feature extractor, local neural network, and the remote neural network. During training, the feature vector of each training data sample is sent to an XAI-based feature importance evaluator. We use an off-the-shelf pre-trained neural network as a reference neural network to ensure accurate importance evaluation. Otherwise, during training, when the local and the remote neural networks are not well trained, the calculated importances will be inaccurate. The evaluated importance scores will be used to construct the XAI loss function as described before. And the training is also supervised by the regular prediction loss function to ensure inference accuracy. The local and the remote neural networks are trained to combine the predictions together for a final prediction. The main issue is that the two predictions may have different scales. So if we simply sum their predictions probabilities together, some small but important prediction values can be overwhelmed by other large but less important values. To address this issue, we introduce alpha that is parameterized by a learnable weight W to combine two predictions as a weighted sum. More details of the hyperparameter tuning can be found in our paper. Besides these training modules, we also pre-process the feature extractor to make the training procedure more stable. Specifically, we rearrange the indices of the feature extractor's output so that most of the features will be already sorted before training. Please refer to our paper for detailed algorithms. We implemented our offline training procedure using TensorFlow and deployed the trained neural networks on a weak microcontroller board and a Dell workstation, respectively. In our evaluation, we use three baselines. MCUNet is the local inference method, and it uses neural architecture search to find the best local neural network within the given neural network complexity constraint. Edge-only inference is to offload all the raw input data to the edge server. Deep cloud and spin are two different neural network partition approaches. We focus on image recognition tasks and use multiple different datasets in our evaluation. For easier comparisons, we configure existing approaches' neural network complexities so that the difference between theirs and AgileN's inference accuracy is within 10%. The results show that AgileN is able to reduce the end-to-end inference latency by 2 to 2.5 times, while retaining similar inference accuracy with deep cloud and spin. More detailed evaluations show that AgileN's latency reduction mainly comes from the lower local neural network computing time, which can be up to 10 times lower. We further compare the feature compression performance with deep cloud. AgileN can outperform by 20% to 70%. These results all demonstrate the adoption of XAI in AgileN allows achieving higher feature sparsity with much lower computing cost. We also compare the AgileN's local energy consumption to other schemes. Because AgileN has more lightweight local neural network and less data to transmit, it saves more computation and communication costs. The results show that AgileN's energy efficiency is 1.6 to 2.5 times higher than deep cloud and 8 times higher than MCUNet. Similarly, AgileN requires much less local memory and storage compared to MCUNet. We also tune the clock frequency on the microcontroller to mimic other devices with lower computing power. The results show that AgileN can have latency reduction by 2.1 to 2.5 times on microcontrollers with different CPU frequencies. And this implies that AgileN can be adopted on various microcontrollers with different computing powers. Due to local resource constraints, many embedded devices use narrowband low-energy radios, such as Bluetooth. Under different bandwidth constraints, AgileN can constantly outperform others and restrain the latency within 100 milliseconds and 50 milliseconds. To summarize, we propose a new neural network offloading technique, AgileN, which leverages XAI to make offloading strategy data-centric and agile. AgileN enables accurate, low latency, and low-cost neural network inference on extremely weak embedded devices. Our work is the first to integrate XAI techniques to neural network offloading systems, and we demonstrate a practical solution to harnessing the power of XAI on weak embedded devices by migrating the expensive XAI computations from online inference to offline training. This is the end of my presentation. Thank you for listening.